Good afternoon to everyone. Myself, Sandeep Singh Chauhan. I am working as an assistant professor in Amrita School of Engineering, and I am collaborating with IIT Delhi to basically work done in the area of vibrational energy harvesting. So today I am going to share some of my research work, which is entitled Flexible Vibrational Energy Harvester with Groove Design using BTO and PVDF film for the higher output. So this will be the outline of my presentation. So I will start with a brief introduction, then what will be the objective of behind this work and motivation, then methodology we used and process flow, followed by simulation and experimental result and conclusions. So we all know that energy harvesting is a very established technology. So whenever we hear about the energy harvesting, we think about the solar cell, windmills, or hydrothermal energy harvesters. So that energy harvesting technology are not suitable, or I can say that it is limited to the the devices which required more power in terms of kilowatt or watt. So to power the low power devices, low wireless power devices, we need a solution for this. So solution for that one is vibrational energy harvesting. So vibrational energy harvesting are mainly three types. So based on the principle electrostatic and electromagnetic and piezoelectric. So I am going to talk about the piezoelectric based energy harvester. So in this you can see that so basically vibrational energy harvesting is the conversion of any type of vibration that is available, kinetic energy that is available in the environment to electrical energy. So like building vibration, bridge vibrations, railway track vibrations, even hands movements, wrist movements of human body can be converted into electrical energy. So this is the process you can see. So available kinetic energy is converted into mechanical vibrations through mechanical structures. Like in this we have used the cantilever structure, and then further that mechanical vibration is converted into electrical AC output. So this conversion from mechanical vibration to electrical AC output will be done by piezoelectric material, and then further that AC is converted into DC using the conditioning circuit, rectifier circuit, and then further conditioning circuit for the useful application. So in the bottom half you can see that the principle of actually I have mentioned the principle of piezoelectricity. So those who are aware, so you can see that a cantilever and with piezoelectric material sandwiched between two electrodes, bottom and top, and when any stress applied on it, it generates a charge across the cantilever. So this is basically principle behind this energy harvesting technology. So this slide I have kept you to just give you the brief glimpse of recently reported work. So you can see that one of the piezoelectric energy harvester cantilever that is based using the aluminum nitride is tested below the bridge to basically monitor, self-power the monitoring of bridge, health monitoring of bridge. And one more literature is reported basically based on the aluminum nitride piezoelectric material to basically monitor the tire pressure of a vehicle. And third one is the PVDF based piezoelectric energy harvester, that is flexible substrate based piezoelectric energy harvester, reported basically to generate the energy from RTL wall of a pig heart. So you can see that this type of energy harvesting technology have a big role to play in the coming future, and this is now in early stage of research. And it has the many applications like IoT devices. So nowadays we all know that a single IoT network has more than 20 millions of sensors. So to replacing the batteries of that much sensor, and also some of the sensor are deployed in beneath the earth, are used in the defense applications. So there the replacement is also difficult. So to solve that problem, this is the one of the best technology we have right now. So we have application in monitoring of sensors, medical devices, and also in large area application. So our objective in this area was to first design a low cost flexible substrate energy harvester with attached proof mass. So in this diagram you can see that we have designed a cantilever based energy harvester attached with a huge proof mass. So, and also we have used a very low cost process method to basically fabricate. First we design, then simulated, and then once we optimize the dimensions of particular energy harvester, we have fabricated using a low cost process technology. And motivation behind this, as I told, it's basically self-powered the wireless sensor node devices, and piezoelectric methods do not require the external input. As in case of electrostatic and electromagnetic, we required in electrostatic we required external input, whereas in electromagnetic we need the magnets, complex magnet to basically generate the output. So that also limit the scaling of the device. Whereas in piezoelectric case, the scaling we can do with the requirement of the chip and future technology. So next we design and then fabricated using a barium titanate and PVDF composite film, using PVDF composite film. So this is the method we have used to basically fabricate the first composite film of barium titanate and PVDF. So first we basically dissolve the barium titanate and PVDF material in DMSO organic solvent, did the stirring for a few hours to basically dissolve these materials, and then spin coated on a molybdenum deposited PET substrate. So it's a polymer substrate on which we have basically spin coated, and then further annealed for get the crystalline, particular crystalline phase, because the PVDF shows the basically piezoelectricity in the beta phase, and beta phase can be obtained at a particular temperature. So basically we anneal to get that higher beta phase and higher piezoelectricity from the deposited material. And this fabricated material, piezoelectric material, we have used to fabricate the energy harvester using laser cut technology. So in this, you can see that in the first step, we basically took the PET sheet, we cleaned it using IPA, acetone and nitrogen, dry nitrogen, and then we deposited the bottom moly electrode. On top of that, we deposited that fabricated highly piezoelectric PVDF BTO composite film, and then further we deposited the top electrode using the thermal evaporation. So for your knowledge, we used basically deposition of bottom electrode using the sputtering system, so that adhesion will be good. And in case of top electrode, we use the thermal evaporation system, because we cannot do the deposition in plasma, because it will damage the polymer film. And in the last step, we basically cut the cantilever structure using the laser cut technology, femto laser cut technologies. And on the right side, you can see that it has a basically energy harvester characterization setup, which consists of basically shaker system. Main part is shaker system, which basically vibrate or shake at a particular frequency and acceleration. And we tested using this shaker system. So we kept mounted our device on this shaker system, and we controlled using the function generator, and so function generator, and also we use the power basically power amplifier is used to basically give the signal to the shaker with the amplification. So this is the method we have used, and below the, you can see that on the right side fabricated piezoelectric energy harvester using the PVDF and BTO film, and on bottom you can see that equivalent circuit. So it has basically a piezo current source acting as a current source connected parallelly with capacitor of the piezo sandwich layer, and RL is the load which we connected to measure the power or voltage across the generated cantilever harvester. So before fabricating, we did the simulations, and we incorporated basically in this the one groove structure. So in A, B, C and D, you can see that different groove size structure is incorporated to basically, why we have incorporated this groove structure. You will see here in the first pictures, you can see that we have basically calculated the stress along the cantilever. So you can see that for the 4 mm gap of groove size, we are getting almost uniform and highest stress. So we need the higher stress in this area to generate the higher output voltage. So that is the reason we have basically simulated the structure with different groove size, and once we optimize the structures, we did the fabrications, and you can see that the fabricated energy harvester is generating 1.1 volt off at a 0.7 G acceleration. So this is the experimental result, whereas simulated result is little bit higher. So it is generating up to 2.8 volt. But we can think of that there could be a loss because of this mechanical structure. We have electromechanical coupling coefficient that is called, so that will also give some loss. And during the coupling of kinetic energy to the mechanical structure, there will be loss. So we can understand. So further we are trying to basically match validate. So maybe we have to create the model which will include the losses, and then we can be able to validate this experimental with the final results. So we have basically characterized the energy harvester using characterization setup at different acceleration. So we have characterized at 0.25, 0.5 and 0.75. So that is understood that it will give that higher output at higher acceleration, because it will give the higher, it will generate basically higher the stress. And further, we have used a Dickson charge pump circuit to basically boost this generated output into higher output, so that it can be useful for the practical application. So in the this circuit you can see that this is the combination of capacitor and diode. So diode are the basically Schottky diodes which has basically voltage drop in the range of 200 to 350 millivolts. And this is the most important part, is that this is the passive circuit. So it do not require any external input, and it can basically amplify, or it can generate it can multiply the input signal. So basically we have in this, we have applied 0.1 volt and we are getting 4.1 volt. So this could be a useful, and this is not only doing the multiplication of the input, it is also with the same time it is also doing the rectification. So with this note, I'll conclude my work. So in this we have basically designed and simulated the different structure with groove design, and used the optimized BTO and PVDF nanocomposite film to basically fabricate the cantilever energy harvester, and use the also integrated the conditioning circuit which generate the voltage up to 4.1 volt. So it has the potential to basically drive the low power sensor devices in the coming like future technology. So that's all about. Thank you.